course. Today we are going to talk about tissue absorption, which is a part of tissue optics. As you have seen in the earlier class, we had talked about the tissue spectroscopy. That is how the each individual photon interacts with the tissue. Today we talk about after this interaction, what happens to the photons. Does it get absorbed or it gets scattered? So these are the main two things that may happen. Either it can get absorbed within the tissue, or it can get scattered. Now, if there are dense scattering, then some of the photons may also get reflect back. Okay, but the two most important thing that happens is absorption as well as scattering. So what you see over here is the absorption that we're going to talk about today. So this is a single photon that you see over here, and this single photon gets inside this tissue, and you can see there's a lot of scattering that occurs. Okay, so and some of the photon may actually come revert back, so this is known as back scattering, and then some of the photon would actually move forward after the scattering, and those are known as forward scattering. Okay, now the question that comes into our mind is like, what is inside the tissue? What are the different constituents inside the tissue which leads into the scattering as well as absorption? Okay, in absorption, you can see that this photon is getting absorbed while it's propagating through the tissue. So in the tissue, there is first interstitial fluid, and along with it, there are a lot of other tissue constituents such as cells. The dimensions of cells are in order of few micrometers. Then you have water molecules. Water molecules are in order of nanometers. Then you have lipids, which are in orders of nanometers. Haemoglobin in order of few nanometers. And then you have collagen fibers. Now, the collagen fibers are like very long structures which have a diameter of 5 nanometers, but it's so long that it can go in order of few tens of micrometers. Okay. In addition to it, there are other tissue constituents like melanin, beta carotene, cytochrome C oxidase. All of these tissue constituents are responsible for absorption and scattering. So the photon which goes inside the tissue, for example, I shine my torchlight or my mobile torchlight into my finger. So all these tissue constituents are going to play a role for its absorption and scattering together. Okay, so now next comes how is it a function of a operating wavelength? For example, I shine my light from my mobile phone. You can see this is my mobile phone, and I shine the light over here. So this is a torch light, and this is a white light. Okay, so white light is kind of a broadband light source. Broadband means it has a lot of colors. So it has red, blue, green LEDs, and which are produced together to give a white color. Okay, so each of the absorber in the tissue has its absorption coefficient. Now we'll talk about absorption coefficient, like how do you define absorption coefficient, how do you define scattering coefficient. But I want to give you an idea how does this absorption coefficient for each tissue constituent varies as the function of the operating wavelength. So whether I shine white color, or I shine a red color, or I shine a green color, or I shine a blue color. So for each of the wavelength, I will have a specific absorption coefficient. Okay. For example, if you see H2O, which is the water, right? The water at 1200 nanometers, or that is in NIR. So let me go to visible range. That is around 650 nanometers, which corresponds to the red color. You can see over here it has around an absorption of around 10 power minus 3. Well, this is a logarithmic scale that you see over here. So it would be around 10 power minus 3 per centimeter inverse, sorry, per centimeter. Okay, so that is the value of its absorption coefficient. Now for various tissue constituents, for example, lipid, oxygenated hemoglobin, and deoxygenated hemoglobin. So if you just see HB, that it means it is deoxygenated hemoglobin. What does it mean by deoxygenated? Means the main purpose of hemoglobin is to carry the oxygen from one place to another. Okay, now if the hemoglobin doesn't have an oxygen, molecule, then it's known as deoxygenated. Now, if the hemoglobin is carrying a oxygen, then it is known as oxygenated hemoglobin. Okay, so both oxygenated and deoxygenated have a very similar absorption coefficient when you go from in visible range. It just starts to break up around 600 nanometers. You can see over here, this is where it start to break up. Till then, it's almost kind of very similar, very difficult to distinguish. But over here around 620, 630, there is almost a 10 times difference in absorption coefficient between deoxygenated and oxygenated hemoglobin. And these are the constituent, these are the kind of a behavior that we kind of look for to quantify the tissue constituents for a particular diagnosis of any disease. Okay. Similar to this absorption coefficient, we have scattering coefficient. So scattering means how much is the scattering that may happen. So we're going to define the scattering sometime. In You can see there is a similar kind of trend throughout this curve, and that curve is that it's kind of exponentially dying down as the wavelength is increasing. Okay, so as you go on tune to higher wavelength, that is, you move from visible light source to NIR, you see that your scattering is kind of significantly reducing. Okay, so the light can actually propagate far more inside. As you can see over here, the scattering is more. Sorry, scattering is more than this back scattering. But if you're if you're operating with a higher wavelength, then there's a lot of chance that you will get forward scattering. Okay. So this is a nice animation from the MIT Media Lab. And what we are doing is over here is we are shining a pulse, a small pulse of a light source, and it's passing through this tissue. And I'm just detecting it with a camera. Now, what I'm giving as an input is a Gaussian, temporal Gaussian pulse. Okay, but what I'm getting on the output is something different. Okay, so the photons which kind of doesn't undergo a lot of scattering, like very few scattering events it undergoes, those are known as ballistic photons. Okay, so you can also see that as your tissue becomes small and small, you will have a more number of ballistic photons. Okay, if you have tissue is kind of becoming thicker and thicker, number of photons which are going ballistic are kind of very less. Ballistic means very less number of scattering events that may occur with those photons. Then there are something known as snake photons. Okay, snake photons are those photons which goes to very low number of scattering. So you can see the green color is for ballistic photons, that it just goes straight. Okay, then you have the snake photons which is in a sky blue color, and then it undergoes few scattering events, not many, very few scattering events. So in the detector, the first that gets detected is the ballistic photon, that is a green color, and then the next is the one that is in sky blue, that is snake photons, very few scattering events that it undergoes through. And then there are other photons which are known as diffuse photons, which undergoes a tremendous number of scattering events. So it undergoes so many scattering events that it may also, some of the photons may actually scatter back, etc. also, right? So these are the three photons that we will be working with: ballistic photons, snake photons, and diffuse photons. Most of the time we will work with diffuse photons because usually the tissue thickness is significantly more, which result into diffusion, that is, you just scattered in different directions. Okay. So here you can see this is green, that is the ballistic photon, sky blue, that is snake photon, and then finally with a very long tail is the diffuse photon, because there are a lot of scattering, and while detecting you will get a kind of a very you also kind of receive the photons after a very long period of time. Again, by long period of time, it's still in order of nanoseconds. Okay, so before we go forward to understand how to quantify the absorption coefficient and scattering coefficient, it is first important to understand the what is the path length and mean free path. How do you define those two functions? Okay, now if you assume you have a tissue which is a square tissue having a dimension of 10 mm, length of 10 mm, and you assume there are three photons which is propagating through the tissue. Okay, so you have photon number A, photon number B, and photon number C. Over here, this photon number A, the red path is the is the path which the trajectory is the path which is traversed by the photon number A. Blue is the trajectory traversed by the photon um, which is the photon number B, and C is the photon. This is the third photon, and the green is the color for the trajectory which is traversed by the photon C. Okay, now again important to know is the tissue length is 10 mm. Now let us see for each of the photon how much is the distance being traveled. Okay, so what we have done over here is that this distance is around 2 mm, and then it just scatters because of the tissue constituents, and then it goes up is 3 mm, and then it's moved down, it's around 5 mm, then 4 mm, 2 mm, then it just comes out, right? So path length, path length is the total mm that is covered by the photon A, right? So the photon A will have, if you just add all of them together, you will have the path length of the photon A. That is how much the for that photon is has traveled in a tissue dimension of 10 mm, right? So similar to this we have for photon B and for photon C, right? So you can see that for photon A, the total path. Okay, so first is total path length and mean free path. Now, what I have mentioned over here is the mean free path. Now, mean free path is defined as the total for each before the interaction. For example, this is the point, is the first interaction, second interaction, third interaction, fourth, and then fifth interaction. Okay, so there has been 5 interaction, and each interaction have how much distance it has traveled before it interacts. Okay, so mean free path is the distance before it interacts. Okay, so now we can also define something known as average mean free path, right? So what we do is that we add all of them distance together and then divide by the number of interaction. For example, it's 2 plus 3 plus 5 plus 4 plus 2, and divide by number of interaction, that is 5. So average mean free path is around 3.2 for the photon number A. Now what does it mean? It means that approximately every 3.2 mm the photon A is having an interaction. Okay, similarly for B, this interaction is around 3.75. There have been only 4 interactions in this case. So for the photon B, every 3.75 mm there is an interaction. Similarly for photon C, you have around 4.2 mm. Now I can just come up with a lot of photons. I can just capture like tens of millions of photons, and then I can come up with a mean free path for the scattering. Okay, so I get it around 3.71. Just now I have added only the average of these 3 mean free path of ABC, but I can have it for tens of millions, and that's how simulation will happen. Okay, so if you are simulating a phantom tissue, for example. Now, what I have defined is mean free path for scattering. Similar to this, as I was talking some time back, is the path length. Now, the path length for the photon A is around 16. For photon B is around 15. So if you just calculate it, 3 plus 3 is 6, plus 4, 10, and then plus 5 is around 15. So a total path length is 15 mm. That is, the photon A traverses 15 mm in a tissue of around 10 mm. Okay, that's very important. This is so it's not ballistic photons. Now for the path, the photon C, it traverses around 17 mm. It's kind of very, very high, right? So now I can come up with a new figure which is known as average path length. Okay, so the average path length, considering there are only 3 photons, it would be just addition of this divided by the number of photons, that is around 16 mm. Okay, so now you have 2 definitions, that is mean free path for scattering, that is the distance that a photon may travel before it scatters or before it interacts with the and changes its direction. Okay, that is important. And second is the average path length, that is uh, how much the on an average does the photon traverse within the photon. Okay, this both the things can be calculated using a detector, individual like single photon detector. Okay, so So now let us go through and try to understand how the photons actually interact with the tissue, and how do we quantify the absorption coefficient and scattering coefficient. Now you can see again the photon is interacting with this tissue. It goes to backscattering and forward scattering, and then gets some of them absorbed. Now assuming now the length of the tissue is changed from 10 mm to 2 centimeter, and this is how you define the path length. Okay, so the total distance which is traversed is going to be significantly more than 2 centimeters, not going to be the same as 2 centimeter. Now you can define this absorption as the probability of absorption per unit path length. So we defined what is path length, so it's probability of absorption per unit path length, or it could be also defined as inverse of the mean free path for absorption. Now we defined the mean free path for scattering. The same thing we can define mean free path for absorption, that is the amount of this the distance which is traversed by the photon before it gets absorbed. Just define it for each and every photon, and then just some average, make an average of it. Okay, similar to this we can also define scattering coefficient, that is probability for scattering per unit path length, that is identical to this, and it is going to be exactly equal to the mean free path for scattering. This is what we have already defined in the last slide. Okay, now in today's session we'll talk about extinction coefficient, that is kind of proportional to the absorption coefficient. So most of the places that you will see might not be having absorption coefficient, but you will be observing the extinction coefficient, but it's kind of directly proportional to this absorption coefficient. So it should be fine. Now let us go and see for each and every individual tissue material, that are tissue constituents such as lipid, collagen, hemoglobin, what is the absorption coefficient. Okay. Now the first thing that we have is the hemoglobin. So as I discussed some time back, this is have it's kind of a globular molecule, and it has two pairs of chains, and in the center it binds with the oxygen. So over here, so if it is with oxygen and if it's without oxygen, it's known as oxygenated and deoxygenated hemoglobin respectively. This is how the chemical structure of the hemoglobin looks like. Now if you shine a broadband light source, that is a pure broadband, a very a uniform broadband light source, which is kind of having a similar spectral pattern throughout the wavelength, and you can get a diffuse reflectance from this. You can actually get the absorption coefficient of the hemoglobin. Now you can see that the guy is piercing a kind of a needle onto the surface of the tissue, and there's blood coming out, so it's kind of red in color. Okay, now the reason why it is red in color is that when we shine a white light, as I was discussing, when you shine the white light, the green and the blue light is getting absorbed in the hemoglobin, and only the red light is kind of scattered back, right? So very less absorption in the red light spectrum. Right now you can also see the same thing when you see the spectrum over here for the oxygenated and deoxygenated hemoglobin. So you can see that very high absorption. This is y-axis is absorption, and x-axis is the wavelength. So it's very high absorption in the blue as well as green regime in the of the spectra, absorption spectra, and very low absorption in the red spectra. That's what you see over here, right? That is the reason that when you shine a white light has all the three constituents: red, blue, and green. It hemoglobin actually absorbs the green and the blue light, and it doesn't absorb the red light. So what happens to the red light, red part of the white compound light? It scatters, as we were discussing some time back. It goes for backward scattering. Some of the light will get back scattering, and then it goes into your eyes, and you actually observe the red light. Okay, so this is absorption coefficient for hemoglobin. Then we go for another tissue constituent, that is known as melanin. Okay, in the case of melanin, this child is suffering from albinism, which occurs when the melanocytes produce very less melanin. Okay, in the case of it becomes white in color. So it actually gives us the color of the skin, that is a little bit brownish color for Asian people, especially from India. So you can see over here what is happening in this. Why we have a kind of a brownish color over here is because when we, again, white light is shining to my skin surface, and the blue light and the green light is getting absorbed, and the little bit of green light is being scattered along with the significant amount of the red light. So very low absorption in the red light, as you see over here, and low medium absorption in the green light. So it kind of merges out the green and the red part. So your orange, yellow, all those things are there and just merge to become a brown color that we have, right? So the absorption is for melanin is kind of dying down as a function of wavelength, right? Now we have beta carotene. So in the case of beta carotene, for example, that is a which kind of again a reddish kind of a material which is present inside our tissue, and what you see is kind of reddish in color, like a rust red in color, and that's again because it has very high absorption in the blue regime. Okay, blue and little bit of green regime. So a lot of red light is being scattered, back scattered, and you it color is actually red in color. So this is absorption coefficient as a function of wavelength for melanin. Okay, then you go for bilirubin. Bilirubin is you will find an infant suffering from jaundice has a significant amount of bilirubin present in the blood vessels. Now, what happens is that because of bilirubin, you can see that it has very high absorption in blue regime. So it reflects the green and the significant amount of red light. So green and red light merge together to have a yellow color, right? So that's why the infant suffering from jaundice, you can actually do a visual inspection and you can say that a person is suffering from jaundice or not, because the skin surface will become a little bit yellowish in color, right? Even the eyes, if you see, it will be a little bit yellowish in color, and with this you can say that this infant is suffering from jaundice, and that is because of the bilirubin. Okay, so each and every constituent of the blood or the tissue has its own absorption coefficient, right? So if a particular tissue constituent is increasing or decreasing, you can identify it based upon the visual inspection as well, and this is one of the examples that you see in front of your screen. Okay, now all of this material constituent that I'm talking about are chromophores. Chromophores means which responds to color. Okay, that is important. So each of so in each of the cases that we discussed till now, each of them were having low absorption in the visible spectrum. That's why it may scatter some color as well. Okay, but there are some other non-chromophores also, which have very high absorption throughout the visible spectrum. Okay, and it will not scatter any color, right? So these are the other chromophores: myoglobin, flavin, and cytochrome C, and cytochrome chrome C oxidase. And now I'm talking about the non-chromophores. So few of the non-chromophores are, first one is the lipid. Okay, now for the lipid, if you see, it has it has very low absorption in the visible spectra. Right, you can see that it's almost nil, or kind of not nil, but it's kind of very less absorption in the visible spectra. Sorry, I by mistake I told it's very high absorption in the visible spectra, which actually has to be lower absorption in the visible spectra. So you can see it's very low absorption in the visible spectra, but very high absorption in the infrared, that is near infrared spectrum over here. Okay, so that is the reason why it doesn't have any color. The lipid, if you see, it's kind of transparent. So the light actually passes through it because it has very low absorption, a lot of high number of ballistic photons and snake photons. Now we talk about water molecule. Now again, water molecule, it has its own vibrational modes over here. That's what you see. And in this case, you can see that in visible spectra. So this is the visible spectra that you see over here. This is the visible spectra, and in this visible spectra, the absorption is kind of very less. Okay, so this is wavelength below UV regime, and this is in NIR. So it has a very typical nature that within this water, within this visible spectra, the absorption is kind of very less for the water. and that is why the water is transparent. The photon that goes through it, it goes through without a lot of absorption. Just scatters, little bit scattering would be there, some kind of reflection would be there, but lot. Okay, so let us go with another non-chromophore, that is collagen. Collagen is is a tissue constituent which gives us the structure that we have for the muscles, and it gives us the strength to pick up some object, for example. So in collagen you can see again, it has this figure, it has both scattering as well as absorption. The absorption is in black color and the scattering is in red color over here. And what you see over here, the scattering is again going down, sorry, going down. The scattering is going down as a function of wavelength. However, the absorption that you see over here, the absorption is very low in the visible range. So this is the visible range, and it's kind of lower. And then at the higher wavelengths, that is in NIR, it's kind of significantly very high over here. These are the three non-chromophores, and this is the figure which encompasses all the different tissue constituents. You can see melanin. We call this on the y-axis is the absorption coefficient, and on the x-axis is the wavelength. Okay, so you have the melanin, you have oxygenated and deoxygenated hemoglobin, you have DNA, you have RNA, you have bilirubin, you have water, you have MbO2, MbR, this is, and then you have lipid, and then you also have collagen, but I don't think so collagen is part of this photo. But yeah, these are the main tissue constituents that you see throughout the tissue, and all of these are happening all simultaneously. You shine a white light and all of these interactions for so many tissue constituents are happening simultaneously, and then you actually see something like a brown color, as well as if you cut open the outer surface of the tissue, you can see a red color, because of the hemoglobin blood actually. Okay, so I hope this gives you a good introduction of how the absorption actually happens with many tissue constituents. We'll talk about diagnosing of a particular disease. For example, it could be jaundice, when you shine a light and you get a yellow color out of it, and then if you can quantify how much is the yellow constituent, then you can actually say how much is the constituent of or composition of the bilirubin, if it is a person suffering from jaundice or not. So all those things you can actually put numbers to it and quantify, and then diagnose a particular disease. For example, you want to diagnose cancer. So in that case, cancer has very lower composition of hemoglobin as compared to normal tissue. So you shine a light and you try to see whether the it has lower composition of hemoglobin or higher composition of hemoglobin. From there, you can actually know whether the tissue is kind of going for cancer. It is actually cancer is occurring over there, tumor is occurring over there or not. Okay. So thanks a lot for this session. In the next session, we'll talk about the scattering. So like this absorption for each and every tissue constituent, we'll talk about different types of scattering. And then we talk about scattering in that we see in real life. That is why the sky is blue in color, why the clouds are white in color. So in the daytime, why do we see the light to be yellowish, the sunlight, while in the evening we see a red or yellow color on the sky. So all of them are kind of related to scattering, and somehow those things are also related once we talk about tissue optics as well. Okay, thank you.